Hey, today we're going to be talking about some searching algorithms for technical interviews. So here we have a bunch oh, here we have a bunch of sorting algorithms and we're going to be discussing their time complexity, their stability, and also if they're an in-place algorithm. So the point of sorting algorithms is to, sort an array of items, whether it be ints or strings, by a certain criteria. And in this case, if it's numbers, we're going to sort in increasing order. So the first algorithm is going to be insertion sort. Insertion sort is going to be iterating through each item and comparing it with its left element. And if the item is less than its left element, then you're going to keep on moving it left until the criteria is fulfilled. So for example, you have this array right here, 2, 6, 5, 3, 8, 7, 1, 0. For our first iteration, we have 2, 6, 5, 3, 7, 1, 0. And we're currently looking at 2, and 2 has no values on the left. Therefore, we can just move on to the next item. We look at 6, and 6, the value that's on the left of 6 is going to be less than 6, so we don't have to do anything there. And so now we can move on to the third iteration. In the third iteration, we're on 5, and we can see that 5 is less than its value or its left neighbor. So now we can move 5 over 1. And we can move on to the next iteration. In this next iteration, we see that 3 is going to be less than its left neighbor. So we are going to move 3 over 1. We once again see that 3 is going to be less than its left neighbor, so we're going to move 3 over one more time. And now we see that 3 is larger than its left neighbor, so we can stop this iteration here. And continuing with our algorithm, we're on 8, and 8 is greater than its left neighbor, so therefore we don't have to do anything for 8. And now we're on 7, and 7 is less than its left neighbor, so we will move 7 over once. And you get the point, so I'm going to stop drawing all of this out. It's getting kind of annoying, but 1 is definitely less than its left neighbor, so it's going to keep on floating back. It's going to see 7. 7 is greater than 1, 6 is greater than 1, 5 is greater than 1, 3, 2, and then it's going to find itself at the beginning of the array. So then after 1 is processed, the array would look like this. And then once again, it's going to move to 0, and 0 is also less than all these numbers, so I think I forgot some numbers. It's going to look like this. So this algorithm has an average time complexity of O n squared, and this is because in a worst case scenario, the numbers, if they're low, because if you look at this example, you had 1 and 0, which really belong on the left side of the array, but in the unsorted version, they're on the right side. So you would have those numbers, like going all the way back, iterating through the entire array to get to the front. And if you had theoretically the worst case scenario, which is a decreasing array, all the numbers would have to flow back in that kind of same fashion, which would leave you with multiple iterations of the array just to sort the array itself. Now we can talk about what stability and in place means. Stability means that when an array has two equal items, array might look like this: 3, 3, 2, 1. And after sorting 1, 2, 3, 3, are we sure that these two equivalent items are in the same order that they were in the unsorted array? So a stable sorting algorithm would ensure that these two equivalent items retain their position. An unstable algorithm would have these two items switched. or the equivalent item switched. In this case, insertion sort is a stable algorithm. And in place means that a sorting algorithm will not make new data structures to sort. It will only alter the array that it's currently processing. In this case, insertion sort is also an in-place algorithm. Furthermore, we know that insertion sort performs really well in almost sorted arrays, so arrays that are close to the solution, and small arrays, which is important for a topic that we're going to talk about later, which is Tim sort. Now, moving on to our next sorting algorithm, we're going to be talking about merge sort. So with this same input array, we're going to perform merge sort on it, and this is going to be a recursive algorithm involving the splitting of this array in half many times over until they're in their single elements. And the way this algorithm looks is it's going to be in a tree format because we are using recursion. So the input array might look like this, and then on the first iteration, you're going to break these two arrays in half. On the second iteration, you're going to break this array in half even farther. And then on the third iteration, you'll have these two elements. And once you've hit singular atomic elements, you're going to pop back up this recursive call stack and at the same time sort the elements. So 2, 6 is sorted, and then once again comes back up here. 2, 6 is sorted, and then you're going to move down to this 5, 3 split into their singular elements. Oh, 5 and 3, and then it's going to jump back up the stack, and this will be sorted to 3 and 5. Jump back up the stack once more. You'll have a sorted array of 2, 3, 5, and 6. Same thing for this side, so 8, 7. And when you return back to your root element, you will have sorted the entire array. So the time complexity for merge sort is going to be O n of log n, making it one of the faster sorting algorithms. It's going to be a stable algorithm, so equivalent elements will retain their position before and after being sorted. And merge sort is actually going to be the only sorting algorithm that is not an in-place sort because you're using recursion and making these new arrays. Python sort and sorted functions are both. So an interesting thing to mention that Python's sort and sorted algorithms are both a variation of insert plus merge sort called Tim sort. So the thing about merge sort is it's one of the faster sorting algorithms, and insertion sort is an algorithm where its edge case of the array that needs to be sorted when it's small or almost nearly sorted, insertion sort will sort it in O of n time complexity in a best case scenario. That combined with the speed of merge sort results in a Tim sort algorithm, which is essentially a silver bullet for, or Python's silver bullet solution to sorting arrays. So now we can move on to bubble sort, and bubble sort is going to be the simplest sorting algorithm, a very beginner friendly sorting algorithm that's also very slow. So here you have your array 2, 6, 5, 3, 8, 7, 1, 0, and essentially the idea of bubble sort is you'll iterate through the array comparing two adjacent values and swapping them if they're in the incorrect order. So for the first iteration, you're going to be looking at 2 and 6. Well, 2 and 6 are prim and proper. They don't need to be swapped. They're in the correct position relative to one another. So we can move on to 6 and 5. Well, 5 is less than 6, so 5 belongs on the left of 6. So we can do that, swap the two. And then we can move on to the next iteration of the algorithm. 3 is going to be less than 6, so 3 needs to be swapped with 6. 6 is less than 8, so we don't have to do anything for that iteration. 8 is going to be greater than 7, so we do need to swap the 2. 1 is going to be less than 8, so we need to swap the 2. And 0 is going to be less than 8, so we need to swap the 2. So from all that, from iterating through the entire array once, we have 8 in its correct spot, and we would have to do that n amount of times to get the complete sorted array, which I'm not going to do because that would take a very long time, and hopefully you get the point of it. So the time complexity of bubble sort is going to be n squared. It's going to be unstable because of all the swapping done, and it's also going to be in place. Overall, just a generally terrible sorting algorithm. Selection sort is going to be iterating through the array and keeping track of minimum elements that can be swapped with the current element being tracked. So you'll need a current pointer and also a minimum pointer. So here we have our input array, and the idea is we're going to keep a current pointer and a minimum pointer, or we're going to keep tabs of these two different kind of elements. So first we're going to start on 2. The current item is going to be 2. We're looking at 2. Can we find something smaller than 2? Well, 1 is smaller than 2. Okay, we keep tabs on 1. 0 is smaller than 2. So we're going to swap 0 and 2. 0 is going to go all the way up here, and 2 is going to go all the way back here. And the rest of the array stays the same. Now moving on to 6. 6 is our current item. And I'm not going to draw the arrow anymore because I just realized that this is essentially the same as all the other algorithms. Can we find an element that's smaller than 6? Yes, 5, and then 3, and then we also have 1. And 1's going to be the smallest, so we swap 6 and 1. And then we're looking at 5. Are there items that are smaller than 5? Well, there's 3, and then there's also 2. 2 is going to be the smallest, so we swap 5 and 2. And now we have 3. Is there an element that's smaller than 3 on the right side of 3? No, there isn't. So now we can move on to 8. Is there an element that's smaller than 8 on the right side of 8? Yeah, there's 7, there's 6, but there's also 5, and 5 is going to be the smallest one out of those 2, or out of those 3, my bad. So 8 and 5 are going to be swapped, and so on and so forth until you get the sorted array. Select sort is going to have a time complexity of n squared. It is an unstable sorting algorithm, but it does sort in place. So quicksort has been excluded from this analyzation of sorting algorithms because I just came up with the worst examples ever. But I will tell you that quicksort has an n log n time complexity. It's not stable, but it is in place.